Hey, welcome back to 2241. Here we're going to do some examples for section 1.5 on lines and planes. So problem number one here. It says find the vector and parametric equations for the line passing through this point and parallel to this vector. And then find two other points on the line, any two other points. All right, so it says find any vector and parametric equations. So let's start by just finding the vector equation. Let's remember that our formula looks like this. R equals R0 plus V times T. And what we need then is a starting point, R0, and a direction vector, V. So let's see, where are we going to get our starting vector through or from? Well, it tells us that the line has to pass through this point 513. Well, that point on the line is as good as any other. Might as well use that as our R0. So we'll take R0 equal to 513. Now we need to know, okay, what vector do I add to this to get another point on the plane? On the line. Well, how about this one? It says that we want our line to be parallel to this vector. Well, if it's going to be parallel to that vector, I can translate that vector onto the line. Remember, you're allowed to translate vectors without changing their direction, and they're the same quote-unquote vector. So we can set V exactly equal to, let's put this underneath. Let's put V equal to, all right, I, J, K, I want coordinate form, so let's put this as 1, 4, minus 2. And now I have that my vector equation of a line is 5, 1, 3 plus 1, 4, minus 2 times t. All right, and now I want parametric equations. So just group up the x coordinates, y coordinates, and z coordinates and write equations for each one. So x as a function of t is 5 plus 1 times t. Y is 1 plus 4 times t. And z is 3 minus 2 times t. And so these are our parametric equations given this vector equation. All right, it says we want to find two more points on the line. So let's just plug in some other values of t. So note if I plug in t equals 0, I get back my starting point R0. So let's find some points R1 and R2. And let's say we choose, I don't know, t equals 1. So R of 1. And this will give me the point 5, 1, 3 plus 1, 4, minus 2. All right, what is that? We get, adding coordinates, 6, 5, and 3 minus 2 is 1. So 6, 5, 1. All right, we need one more point. Let's choose minus 1 maybe. Now we have 5, 1, 3 plus negative 1, negative 4, and positive 2. All right, so now we have 4, negative 3, and 5. And that is another point on our line. All right, and that's it for problem one. So we found our vector equation by specifying a starting point and a direction. These were basically given to us. And we just broke it into its components to find the x, y, and z parametric equations. And then to find other points on the line, we just plug in specific values for t and then add things up. All right, problem number two. We want to find the vector or any vector and symmetric equations for the line through these 2 points. And then they asked us, when does the line hit? It's not super clear, sorry. When does the line hit the XY coordinate plane? All right, so let's find our vector and symmetric equations first, and then we'll answer that question at the end. All right, so our vector equation, remember, we're given 2 points now, and if you look at that table in the previous video, we have that we can choose any one of them as our starting point. I don't know, let's choose A, and it's a vector. All right, and then 2, 4, minus 3. And then, well, we need our direction vector V. What do we do now? We take our vector B, our point B, and use it along with A to make our vector. So we get 3 minus 2 is 1, -1 minus 4 is -5, and then 1 minus -3 is 4. Okay, so that'll be our direction vector. And our vector equation will be 2, 4, minus 3. Actually, I'm going to write this vertically. So I'm going to write this as a column vector, minus 3. And then plus 1 minus 5, 4, t. All right, so there's our vector equation. And remember, we want to turn that into a symmetric equation. I haven't shown you how to do that yet. So first, we're actually going to turn this into a set of parametric equations. Now that's pretty straightforward. We've already done this. We have x equal 2 plus 1, y equal 4 minus 5t, or sorry, 2 plus t, z equal minus 3 plus 4t. All right, so there are parametric equations. And now here's how we find our symmetric equations. We solve for t in each one of these 3 equations. So what we'll get is t equal x minus 2, t equal y minus 4 over -5, and t equal z plus 3 divided by 4. And now note these are all equal to t. So they are all equal to each other. And that means that we can write our symmetric equations as this. Notice that I moved things around a little bit. I didn't write the 1 direction number underneath here, and I took that negative and flipped it, or used it to flip the order of the top subtraction there. And then here I have a plus. So symmetric equations can be given to you in sort of strange looking ways, but it's up to you to remember that the formula says, all right, I have to have x minus something divide by that direction number. Well, x minus 2 is the same as x minus 2 divided by 1, so 1 is my x direction number. Over here, oh, I need to know that I have, or I know that I need to have y minus something. Here I have something minus y. So I need to take a minus out of both of these and put it into the direction number on the bottom. So my direction number is not 5, it's minus 5. And then for z here, I know I need to have z minus something. So this should be z minus -3. And my z coordinate of my starting point is -3, not +3. All right, so some stuff that can go wrong and you want to be careful of. All right, now let's answer that second part. When does the line hit the XY coordinate plane? All right, well, what is true of all points on the XY coordinate plane? So the XY plane is all of the points where the z coordinate is 0. So all I have to do is set my z coordinate to 0, and I should be able to get exactly what I want. Well, if I set my z coordinate to 0 right here in my symmetric equations, what does it look like? Well, I get x minus 2 equal 4 minus y over 5 equal 0. Oh, wait, but then that just gives me x minus 2 minus 4 minus y over 5 equals 0. And that looks like an equation with 2 variables. How is that going to give me a point? Well, it's not. I made a mistake. You can't just subtract this and then say, all right, well, this whole thing is equal to 0 now. Okay. It's true, but you have other equations as well. So what we want to focus on is not that part. Oh, and it's not 0, I'm sorry. It's 3 over 4. If you set z equal to 0, then you get a 3 over 4 there. So oops. If we set z equal to 0, we now have two equations. X minus 2 equals 3 over 4, and y minus, or 4 minus y over 5 equals 3 over 4. So let's write those down. We have x minus 2 equals 3 over 4. That's pretty easy to solve for x. We get 3 over 4 plus 8 over 4 is 11 over 4. So that'll be our x coordinate. And now we have 4 minus y over 5 equal 3 over 4. That one's a little trickier to solve, but you get y equals 4 minus 15 over 4, and that'll be 16 over 4. So we have 1/4 for our y coordinate. And so the point of intersection with the xy plane is 11/4, 1/4, 0. That is our solution for problem number 2. All right, next up is problem number 3. Here we want to show that the lines given below are skew. Now, skew means that they are non-intersecting and non-parallel. All right, if we look at these lines, L1 and L2, we're given parametric equations for each of these lines. Now, they have different parameters here, and that should have been a T, not an S. Different parameters here, T and S, but that just is to keep us from coordinating the motion along each line. We want those lines to be moved. We want to be able to move points along those lines independently. So how do we find out if these guys are skew? Well, we have two things to check. Are they non-parallel? Are they non-intersecting? If they're parallel, then their direction vectors should be the same. So what we can do is take these lines, write them in their vector form. Maybe we'll do this underneath, actually. So let's do this down here. So R1 is 1 minus 2, 4, plus 1, 3, minus 1, t. All right, see how I did that? I know that this, and this are my starting coordinates, and 1, 3, and minus 1 are the coordinates of my direction vector. Do the same thing for R2. I have 0, 3, minus 3, plus 2, 1, 4, S. And, well, now I have two vector equations, and I know that the second vector, the one paired with t and the one paired with s, is the one that gives me my direction. And all I have to do is check that these are not parallel. Well, how do I check if things are parallel? I know how to check if they're perpendicular. If they're perpendicular, I do the dot product and get 0. Parallel, I use the cross product. So let's check 1, 3, 1. Let's write it this way. I want to do the cross product between these two. So we have 1, 3, minus 1, 2, 1, 4, I, J, K. All right. So if this cross product ends up being 0, they're parallel. If it doesn't, they're not. All right, so let's see. I do my cross product. Remember, I do the determinant of that minor. So 3 times 4 minus -1 is 12 plus 1 is 13. Okay, and then I'll do this minor. So for J, I like to do a shortcut where I actually go in the opposite direction instead of doing 1 times 4 minus -1 times 2 and then swapping the order of those, putting a minus in front. It's easier for me to just do minus 1 times 2, subtract off 1 times 4. All right, so that's -2 minus 4 is -6. And at this point, I can already tell this is not going to be 0. And we thus do not have parallel vectors. But let's finish it out just to get some more practice with the cross product. 1 times 1 minus 6 is -5. All right, and so there is our cross product vector. This is not equal to the 0 vector. And so L1 and L2 are not parallel. Okay. So now we have one more thing to check. Are these lines intersecting? How do I check if two lines intersect? Well, I see if there's a way that I can solve the equations to get them, or to get a solution. So what do I do? I see if, I see if I can get the x coordinates. 1 plus t. Okay, so let's come back over here and we'll take a look at these. X coordinates, 1 plus t and 2s, I want to set these equal to each other. And then same for the y coordinates and the z coordinates. If I set those all equal to each other, then I can try and solve the resulting equations for t and s. And that would tell me that, okay, yes, there are values of t and s, which give the same points in both cases. 4 minus t here, and then -3 plus 4s. All right, so we have 3 equations in 2 unknowns. We should be able to solve these. Now, this probably takes a little bit of cleverness. It's easier to pay attention to things that cancel out easily. So t and -t, which means I can just add the top equation and the bottom equation together to get 4, 5 plus 0t equals, let's see, -3 plus 6s. Okay, and that allows me to solve for s. And so I get 8 over 6 is s equals 4/3. Okay, so there's my s value, and I can use that in one of the other equations to get a value of t. Why don't we use the one that, or one of the ones we started with? So we get t equals 2s minus 1, and that means that we have 8/3 minus 3/3 is 5/3 for t. Okay, so that should work for the top equation and the bottom equation, which looks like we may have intersecting lines here. But remember, we have this third equation in the middle, and if these solutions, which are the only ones that work for the top and bottom, don't work for the middle, then we can't have any solutions at all. So let's check. -2 plus 3 times 5/3. Is this equal to 3 plus 4/3? Well, I don't know. Let's find out. So 3 cancels with 3. That gives me a 3 on the left side. And here I get 9/3 plus 4/3. That is 13/3, and these are not equal. So there is no solution, and thus L1 does not intersect L2. This is how you say that. L1 intersect L2 is equal to the empty set. There are no points if you try to intersect those. All right, so that's our problem number 3. Last one on this page, problem number 4. We want to find an equation of the plane through 2, 4, minus 1 with this normal vector. This is our first example with a plane. So what do we do? Okay, well, I'm given a point. I'm given the normal vector. Let me write down my equation for a plane. N dot r minus r0. This equals 0. Okay. Well, what is r0? That's my starting point. Oh, they give me a point that has to be on the plane. Okay, so let's take that as our starting point, as our r0. N is given to us, and that's it. So we have 2, 3, 4, and then times r, which is x, y, z, minus r0, 2, 4, minus 1. And so that has to be equal to 0, which means that we get 2, 3, 4 dot x minus 2, y minus 4, z plus 1 equals 0. Okay, so that is our vector equation of a plane. We can go ahead and multiply this out, might as well, and get our scalar equation. So we have some practice. 2 times x minus 2 plus 3 times y minus 4 plus 4 times z plus 1. And then to get our linear equation, we just want to go ahead and multiply all those constants through and then collect like terms. So 2x plus 3y plus 4z, and then we have minus 2, minus 4, 2 times 2 right here, and then minus 12 plus 4. So the 4's cancel out, and we just get minus 12 there. And this is our linear equation of a line. So scalar, linear, of a plane, and vector. Okay, So this video has gotten a bit long. I'm going to break it up into two pieces. We have another page of examples to go through, and those will be in a separate